Um, we'll be. Is this working for people on Zoom? Okay, cool. Hello. Okay. So we'll start today with one of ours. So we'll be hearing from Jaya Maithil. I try. And she'll be talking about investigating the X-ray jet emission mechanism of two radio-loud quasars at redshift 3. So she's a postdoc here, and her research focuses on understanding the physics of quasars and active galactic nuclei through radio, optical, and X-ray observations. She earned her PhD in physics from University of Wyoming in August 2022. And her thesis improved the statistical measure of quasar orientation and their black hole mass estimates, and also illustrated the X-ray and optical UV properties of some of the most highly accreting quasars. Following her PhD, she joined here as a postdoc under Dan Schwartz and Anita. And now her focus involves detailed investigations into the extended X-ray jets from quasars to unravel their emission mechanism. So thank you, the floor is yours.
Thank you, Anna, for the lovely introduction, and thank you to the organizing committee for giving me this opportunity to present my research today. So good afternoon, everyone. My name is Jaya Maithil. I'm a second-year postdoc in the High Energy Astrophysics department here at CfA. And in today's talk, I'm going to present two very interesting radio-loud quasars, which are at redshift of 3. And they show these extended X-ray emission. And as it will unravel that their radio counterpart for the jet is missing. So I'll be presenting their X-ray data as well as radio data. And finally, I will present some preliminary results on the mechanism of their X-ray emission using inverse Compton of CMB photons. So before diving into the nitty-gritty of the project, I would first like to motivate why we should study, if it goes, why we should study jets. So as we all know that almost all galaxies host a supermassive black hole at their center. And in some of them, these black holes are actively accreting matter and giving out radiation. In 10 to 15% of these active galactic nuclei, we also see these relativistic jets that extends out to megaparsec scale, influencing the environment around it. So they will be influencing the galaxy, their host galaxy, as well as can influence their cluster environment. So it is pretty well known that jet plays a very important role in preventing catastrophic cooling flow collapse in galaxy clusters. And in this way, they are impacting. So whatever is going around in the vicinity of the supermassive black hole, that activity is able to transport energy and matter through this jet to these galactic as well as cluster environments. Now, Chandra has given us X-ray eyes to look at the jet power as well as the morphology of these extragalactic jets. So here I'm presenting the Chandra image of a radio-loud quasar, which is at a redshift of 2.5. And as you can see, we are seeing 3 different components here. So at the optical position of the quasar, we are seeing an X-ray core. We are also seeing this X-ray jet, extended X-ray jet. And there is another third component, which is over there, which is a hotspot in the X-ray. Now, out of so many jets that are being discovered by Chandra, I chose this particular object because this is an example of a jet in which, again, you will see that the extended jet emission is only present in X-ray and the corresponding extended jet in radio is missing. But what can cause X-rays in these jets? So there are 2 candidate mechanisms. One is synchrotron emission, which is just relativistic electrons that are spiraling around magnetic field. they can give out X-ray emission, but for this to produce X-rays, we need highly magnetized jets. So if their magnetic fields are around hundreds of microgauss, they can produce X-ray via synchrotron process. And also in that case, the jet will be much slower at kiloparsec scales. The other competing mechanism is inverse Compton of CMB photon by the synchrotron emitting electron. So if there is a low energy CMB photon, it can get upscattered to X-ray energies via an electron that is emitting synchrotron. Now this is more favorable because if the jet is pointing towards us, it will see a Doppler boosted CMB emission, and in this case, the jet can be highly relativistic, and there is a very minimal energy dissipation expected over subparsecs to kiloparsecs. So as it turns out, there are factors that favors X-ray emission via ICCMB at higher redshift. So the cosmological diminution will decrease the surface brightness of both X-ray region as well as the radio region. So X-ray brightness will also decrease by 1 plus z to the power minus 4, but it will be compensated by a equivalent increase in the cosmic microwave background energy density. So the radio will decrease by 1 plus z to the power minus 4, but the X-ray will be compensated by the increase of CMB energy density by the same factor. One more factor that is more that's favoring our X-ray emission via ICCMB at high redshift is that the electron lifetime of X-ray emitting jet via ICCMB has a longer electron lifetimes than the lifetime of the electrons that are producing radio jets via synchrotron. So the jet that I showed earlier is again shown in this image. So the color plot is the X-ray observation, and the radio data is in the green contours. So you can see that for this particular quasar, you see that only the core and a knot is observed in radio, whereas there is no particular observation, there is no extended radio jet seen in this image. So this is kind of favoring that because it's at higher redshift, the ICCMB is the mechanism that is producing this X-ray. So the two quasars that I'm presenting today are also belong to this class of objects with dominant X-ray jets and almost missing radio jets. So we selected our quasars from the parent sample of 123 radio loud quasars that were selected by matching the Sloan Digital Sky Survey quasars with the first quasars. We put flux density cutoff of 70 millijansky for the radio and a redshift cutoff of 2.5. So this, out of these 123 radio loud quasars, 61 showed extended emission. So we made further cuts on, so we only selected quasars that showed triple radio sources because excluded quasars that show triple radio sources. So if there is triple radio source, means you are seeing a core, you are seeing a jet, and you're seeing a counter jet. But we want to look at the quasars whose jet is pointing towards us. So the jet will be boosted and the counter jet will be deboosted. So you will ultimately see only one-sided jet. So that excludes 31 quasars. We also increased the redshift curve to 3, and we excluded 2 quasars that were known X-ray sources. So that left us with 14 radio loud quasars. So in 2020, we did a snapshot Chandra observation, and we found that only 2 of those 14 show candidate X-ray jets. So today I'm going to present the follow-up Chandra observations of these 2 quasars. They are much deeper. They are 88 kiloseconds and 84 kiloseconds. And last summer, we also obtained 6 gigahertz VLA images in the A array that provided us a spatial resolution of 0.3 arc seconds. So it is very comparable to the Chandra. So now we can actually look at the regions where we think the jet is and compare their X-ray and radio emission. So here I present the VLA image. On the left is for J1405, our first quasar, and on the right is the J1610 is the second quasar. So let's focus on the first quasar. So we see that it has a core of 23 millijansky, and it has a very flat radio spectral index of minus 0.16. Now, this core and the knot, as well as the hotspot that you see over here, was known previously, but with our high sensitive observations, so we are getting a noise of 23.5 microjansky, we are able to confirm that this hotspot is real, but in the previous observations, the sensitivity was very low. Okay, so the knot which you see here is 25 millijanskys, and it has a steeper spectral index, which is expected from the core. The hotspot remains very faint. It is only 1.6 millijansky, and because of that, we were not able to constrain its spectral index. Now moving on to the second quasar, we see that its core is a magnitude less bright than the first quasar. It's only 54 millijansky. And also we see that it is a much steeper core. It has a spectral index of minus 4.2. We see the northwest hotspot, which was known previously, but we are seeing much more structure into that hotspot, which was not present in low sensitive radio images. And the spectral index of the hotspot is like -1. We also, for the first time, found a counter hotspot for this object, which is very faint. It is only 0.45, and we do not have a constraint again for the spectral index. So now moving on to the radio data. So here I'm showing the 500 to 7,000 electron volt band of Chandra. And these images are binned by half a pixel. So that gives a more comparable resolution to the Chandra images, to the VLA images. And I'm marking the core region in circles of 0.95 arc seconds, and the arrow represents the direction of the jet that we see in the radio images. Now, as you can see that the PSF of the observation is very smeared. So it is really hard to say if the X-ray that we're seeing in the jet direction is from a different component, or it is only scattered from the core. So to decipher that, we simulated the images of the core using the core spectral index. So we made 1,000 simulations of, we made 1,000 ray tracing files using SEO trace, and then we projected those files to the detector plane using marks. Now, in doing that, we have to assume a aspect solution. And in literature, there are different values present. So ranging from 0.7 to 0.288. So we want to know which aspect blur solution will give a PSF that is closer to our observation. So we tried these for different values. So here I plot the enclosed count fraction on the y-axis and the radius in pixel size in the x-axis. So remember that 1 pixel is 0.492 arc seconds. And you can clearly see that none of these simulations actually is able to represent the data that is shown in black here. So the PSF of the observation is in black and the simulated ones are in colored. So none of them is a good fit, especially the 0.07 and the 0.15, which are in green and cyan, are producing very narrow PSF than the observed. The good contenders are the 0.20 and 0.288. So what we did is we used the simulations with 0.2 arc second aspect blur to compare our observations with the simulated image when we are looking at regions that are less than 0.7 arc seconds from the core. And for regions outside it, we are comparing our observed image with the simulated image using aspect blur of 0.288. So here I show the observed and simulated counts as a function of position angle. So we use three annulus regions, and we divide each annulus into 12 sectors, each of 30 degrees. And then we compare the counts in each sector that we have observed and what could be scattered from the core, which comes from our simulated image. So as you can see in red here, there is asymmetry, azimuthal asymmetry in the simulated image. So PSF is not very symmetric. And we only find one sector. Only one sector here at position angle of 315 that show a significant excess. So we have detected that there is an extended emission with 5 sigma, in this case, it is 8 sigma detection. Similarly, we do the analysis for the other object. And for that, we find that the extended emission is detected in the position angle of 225, which is marked here. And this is like a 5 sigma detection. Next, we compare, next we looked into the surface brightness profile along the jet direction shown in this pi sector, pi region here. And the red circle shows the counts, the surface brightness in the observed image, and the square shows the surface brightness in the simulated image. As you can see that as the radius increases, we are seeing an increase in counts from an excess in counts in the jet region. We also compared this with the surrounding, like if we move the pi region around in a 360-degree, how the distribution of the observed and simulated surface brightness will look like. And we see that in most cases, the simulation and the observed surface brightness matches, and only in the outer radiuses, we see a clear excess in extended emission. And so now I'll just summarize some of the X-ray properties here. So we fed the core with a single power law with galactic absorption to get the photon index. We find a very flat photon index. The core is very hard. It has like hardness ratio of minus 0.02. We see that the jet, which is shown in this box here, we again fitted by a power law with galactic absorption, and we see that the flux in the jet region is only 2% of the flux seen in the core region. And for 1610, the cores are pretty similar. The core of 1610 is very similar to the first quasar. The count and fluxes are very similar, as well as the photon indexes are very similar, but the jet is very faint. We only have like 7, 8 net counts in here. So we don't have a good constraint on the photon index because the counts are very low. And within the errors, both are kind of same. But in this case, the jet is only 0.4% of the brightness of the core. Okay, so now we have the X-ray flux densities, X-ray measurements, as well as the radio measurements. So what we can do is we can determine the minimum energy magnetic field that can produce the radio emission that we are seeing. So without going into the details, it depends mostly on the flux or luminosity, and you have to assume the shape of the jet. So we are assuming a cylindrical jet, and we are assuming a spectral index of 0.7. We are also assuming that the jet radius is 3 kiloparsec, and we say that the synchrotron electrons have a power law distribution, and we assume a gamma minimum and gamma max. Then we also evaluate the magnetic field that is needed to produce X-ray to the radio flux that is being observed. So once we have that, we transform both these magnetic fields to the source frame, and then we equate this because the magnetic field has to be same in order to produce the radio as well as the ratio of the X-ray to radio. So we don't have a constraint on the theta, so we can solve this equation for trying different values of theta and then get back all the values. So we found some constraints on the bulk Lorentz factor. We see that J1405 has a much higher bulk Lorentz factor ranging from 3 to like 17, 18, whereas the J1610 is much slower. It's the bulk Lorentz factor is much smaller. And also we found constraint on the Doppler factor. So if the angle of inclination is above 10, then the beaming will be more in J1610, whereas there will be less beaming in J1405. We find that the magnetic field in J1405 is much stronger. So it varies from 20 to some 100, less than 100 microgauss, but it's still in the range of ICCMB model, which has been seen before. And the magnetic field for J1610 is much small, is only like few tenths of microgauss. Here we also find the limits constraints on the kinetic flux, and we again see that they are comparable to what is being seen at these redshifts. One more interesting thing is the electron lifetime. So on the left is the electron lifetime of radio emitting electrons, and on the right is the lifetime of X-ray emitting electrons via ICCMB. So as you can see that in both the cases, the X-ray emitting photons have longer lifetime than the radio emitting ones. So this makes sense because we are only the X-ray emitting electrons are surviving, and that's why we are seeing the X-ray jet extended emission, but not the radio extended emission. So since we did not get any constraint on the theta, so what we did, we also compared our model, the results that we got with an already existing code. It's called JetSet. It's an open source code, and it lets you plug in the parameters and choose which models you want to fit. And because we only had 2 data points, one in radio and one in X-ray, we could only constrain 2 parameters. But still, we were able to see that the synchrotron, which is shown in green, and the ICCMB, which is shown in purple, fits the SCD of our quasar, the quasar jet only. And then we ran a MCMC simulation to get the average values of the bulk Lorentz factor and theta, and we find that it is 9.73. Theta is the line of sight angle is 9.73, and the bulk Lorentz factor is around 7.7. And again, for the next one, we find that the theta is like 12 degrees and the bulk Lorentz vector is around 9. So with that, I will leave with the conclusion, and we'll be happy to take any questions. Thank you.
Questions?
Can you remind us the definition of the radio spectral index, and it's a ratio of 2 fluxes, but
Yeah.
which way does it go and what's positive and negative?
So if you have flux density on the y-axis and frequency on the x-axis, a negative value means it's steep like this. And if it's positive or 0, it's like this, and positive. Sorry, if it's 0, it's like this, and positive like that. So negative means as you go to higher frequency, the radio flux is decreasing.
Questions? Well, if there aren't any questions, or also if you have more questions, you can also meet with her. We have like plenty of time slots available. Thank you. It was an
Thank you.
amazing talk. Let's thank the speaker again. So our second talk, it was very last minute but fortunate talk. we're going to be hearing from Dr. Jing.
Jing.
Jing Ye, I'm sorry.
It's okay.
He's an associate professor in Union Observatories of Chinese Academy of Sciences. And he completed his PhD in 2015 in mechanics and energetics at the University of Lorraine in France. And his current interest is focused on the numerical simulation of turbulent reconnection in the solar eruptions. He plays a crucial role as a key member of the Strategic Priority Research Program of the CAS, where he leads the simulation team dedicated to investigating extreme solar flares. So thank you, and the floor is yours.
Okay.
Yes.
Thank you for the introductions. And hi everyone. Thank you for having me here. I'm very glad to share a little some of our numerical work about solar eruptions in recent years. Our topic is about the turbulent magnetic reconnection during the solar eruptions. So if you also please feel free if you have some questions, just interrupt me. So my talk has simply three sections: a background, simulation results, and conclusions. As we know, solar eruptions is the most energetic events in the solar system. It has three typical phenomena, like solar flare and the erupted prominence, and also a CME in a larger scales. It is believed that the solar eruptions is the source to drive the space weather, so it's very important to study it. More and more observations on the left, observations and the theory models suggest that there is a very long, sorry, can I use the mouse? No. There is a very long and thin current sheet connecting the flare and the CME. That is the key region of magnetic reconnections happening here. So magnetic reconnection converts the magnetic energy into the kinetic and the thermal energies of plasma, and also allows for the particle accelerations. It has some classical models like sweet park models. It describes a very long and thin connecting regions. In this model, it only the reconnection rate is very slow, so it's only can use for the some slow reconnection event like a streamer on the sun. And that is the Pichak model. It describe single X-type reconnection regions. This reconnection rate can be very fast, so it's also useful, very useful for explain the fast reconnection events like flares and CMEs. Last one is the right now the most popular one, the turbulent reconnection. It's an even faster way to have the reconnection happen. So, however, to support successful eruptions, we need a fast enough reconnection rate. Forbes and Priest have analyzed analytically the model. That's the catastrophic model, and if they suppress the reconnections, the erupted slope will stop at higher positions. So we need a little bit bigger reconnection rate to have a successful eruptions. So Lin then analyzed this model further, and he concluded that we have like for example magnetic reconnection rate like in this region we can have confined eruptions, and then the reconnection rate greater than 0.005, we can have successful eruptions. That means the quasars can escape from the solar surface. So you can see if it's this value is very small, but we can only have the flux zone bounce up and down, but no eruptions happens. That is the example of this the field eruptions. We can see that the flux zone stop at higher place because the reconnection rate is not fast enough. And so in the past few years, the faster reconnection mediated by turbulence is widely studied and by the plasma physics field. They describe mainly the homogeneous turbulence in ion scale. It's a very small scale, but in our case, that the turbulence is very large scale. That's the flare scale, and it's kind of inhomogeneous turbulence. And in the for example, for the CMZ observations in white light, we can observe the blobs in the current sheet. That could be the turbulence. And from the theory, turbulence theory, we also believe that in the current sheet, the plasmoid could be the fractal structures in different scales, which transfer the energy very efficiently from large scale to small scale, and the Terry mode or the plasmoid can give rise to a higher diffusion rate around the plasmoid. So in our team, a few years ago, in our team, the member in Yunnan have made some attempts to simulate the 2D and 3D plasmoid inside the current sheet. That's the 2D result. That's the 3D result. So in 2D, the plasmoid could be like roughly round, and in 3D it's a flat tube-like. So the general shape is very alike with the observations. Shen also did a simulation before to prove that in the flare we have some plasmoid instability to achieve a very fast reconnection rate suddenly from the appearance of the plasmoid. That gives a very high diffusion rate. Also, on the other hand, the observations right now give some evidence that, for example, Maithil and Shen, they reported the September 10th, 2017 event. The intensity along the CS, the current sheet, in space and in time, all show like a power law distributions. That suggests that the turbulent reconnection might happen in this case. Also, for the plasma heating, the temperature non-uniform temperature distribution, and also the non-thermal velocity along the current sheet in different time varies a lot. So our study aimed to understand the turbulence, how the turbulence play a role for the faster reconnection, and also the UV features found in solar eruptions. So here come our simulation. So the first subject is the turbulent heating in the solar flares. In this case, we solved the single fluid MHD equations, including necessary physical processes. We used this code Athena before. So the basic model is the standard flare model in 2D. So the first work is to study the role of turbulence for heating plasma in eruptive solar eruptions, solar flare, sorry. So the on the top is the observations. We have the observe the heating in in the current sheet and also around the flare in different UV wavelengths. That's the simulation we done. On the left is temperature, on the right is the density. So it's very alike. So we based on the simulations, we made the synthetic UV images, and you can watch this movie we done in different UV waves. So the instability happens in the current sheet, and it collide with the flare loops intermittently. So it's heating can cause turbulent heating on the top. So we also analyze the source of the we can observe the QPP signals. That means the quasi periodic pulse signals at the top of the flare. We analyze the source and the periodic time. So it's very consistent with observations. We believe that the turbulent heating could be the one important source of QPPs. And just we published this paper half a years later. Savanta teams report a flare event that proves our theory. They observed the uncontinuous heating on the top of the flares. And the second extended work is based on the theme of simulations. We observed, analyzed the superarctic fans above the flare loops. We can observe above the flares, there's a hot and diffuse region that we call the SCF structures. And in observations, people often observe that these SCF structures in UV images and also in hard X-ray images, they have like a ascent first and a descending trend, but we don't know why. So based on our simulations, we can explain this. We analyze the time space images for example the density, temperature, and the velocities in different directions, and the Mach number and the divergence velocity. We observe that that A means the place of the SDF, and B means the later position. C means the post-flare position. So we have the same chance. So we just analyze the force imbalance here. We found that okay, that position, that trend is due to the force imbalance between the Lorentz force and the pressure gradient force. We also use the streamline tracking method to analyze where the SAF material comes from. So we found that the materials of structure of the SAF is transported by a reconnection process, and the source of the material is around in the corona background, and it heated in the current sheet. So we conclude that this SCF formations is related to the turbulence heating also in the current sheet and on the top of the flare. And another extended work is based on the same model. We simulated the same model, but use higher revolutions. In this case, we don't include the cooling system mechanism. So we found that the diffusion, that's the diffusion happened here. We found that because of the plasmoid instabilities, the diffusion we will get very high, like 10 times high, bigger than before. That gave a very higher extra diffusion in the current sheet. And we just tracking two plasma merging process. When the two plasma merges, we have like multiple X and O point and secondary small current sheet between them, and we have we follow these processes. So by using the spectral analysis, we analyze we obtain the spectra of magnetic energies along the current sheet. That's that's time before merging, and that's the merging happening. So before merging, we have only one single polar law behavior here, and the time for merging, we have like a double polar law here, and the this turning point corresponds to the Kolmogorov scale. Also, that's the scale for the energy dissipation happening. So we calculate this scale. We have like 100 to 200 kilometers. So that's correspond to the weight of the secondary current sheet between the two merging plasmoid. That means the dissipation can happen at the macro or MHD scale, not like the theory you said only happened at the ion inertial scale. Also, we use this value to calculate the inertial Taylor scale, which gives like 1,000, 2,000 kilometers, which correspond to the global full width of the current sheet. Also, which is also consistent with the observations.
What's the spatial resolution?
Sorry?
What is the spatial resolution?
Oh, spatial resolution. This one is like a one cell correspond to like a 20 kilometers something. Yeah. So it's a very fine resolution already. And the second one, we use the catastrophic model in 2D. We also solve the MHD equations, including some necessary processes using different code as Nirvana and MWAC, because we want to use the adaptive mesh refinement method. That's to get to also capture the file structure in the current sheet. So we use these two codes. So the first one is we analyze we studied the CME heating and the shocks triggered by the turbulence in the CS. And on the left is the observations. We observe the three component structures in the early stage of the solar eruptions. That's the core, bright core, and the bright front, and the cavities. So with our simulations, we also have the aesthetic images in 2D, and this the images, and that's temperature and densities. This is very like. We calculate the energies dissipating at the bottom of the CME. We prove that okay, we got the heating rates so big enough to support the CME heating, even though far from the solar surface. And also we observe the generation of the coronal wave trains around the CME because of the plasmoid collisions. That's the divergence of the velocity. So the reason is that we observe it forms always like a downward or turning fork structures under the CME. So we have this fast mode waves that could be that could be observed in the observations in the future, maybe. And another extended work is that we use the same model. We analyze the QFP waves. That means the quasi periodic fast propagating fast waves. And so in general, most solar fixed physicists believe that the CME shocks could be generated from the rising flash lobe. So it's the motion determine the generation of the shocks. But in our case, we proved it's not. The QIP waves generate mainly inside the flash lobe. That's because the internal disturbance happened inside the flash lobe. Like the B means the boundary of the flash lobe. The P means the perturbation inside the flash lobe. So you can see the waves just leaks from the flash lobe. So compare with observations, that's the observations we had, and the simulations we got here. So it's very like. So that's changed our mainstream point on generation of the shocks, semi shocks. Sorry. And the last subject is about the 3D simulations of the turbulent reconnection in solar eruptions. So in this case, I use 3D. We extended our former 2D work to 3D. So we use the similar method, but we use different 3D models. That's TD model. Initially, it has like a fast loop in the corona, and it erupts due to the loss of equilibrium. So in this case, we just achieve like a quite fine revolution simulations here. So the first conclusion is we want to reperform the 3D images of current sheet in observations. So we use this model, and that's the simulation we did. That's the current sheet, the our surface, and you can observe a lot of details in that. That's the margins plasmoid and different reconnection processes. So we observe that in 4 specific regions along the CS, like in the flat roofs close the principal X point, far from principal X point and the CME. We have different spectra of the velocities. So in general, in the flat roof and the CME, we have like quasi isotopic turbulence, like Kolmogorov turbulence, and in B and C regions, extremely anisotropic. We also analyze, we track like some plasmoid downward and upward. We found different reconnection processes. In the downflows, we observe that the turbulent, the plasmoid reconnection always dominates, and in the upload regions, that's the no plasmoid turbulent reconnection always dominant. So we imply that we can have multiple reconnection mechanics happens in the same time. And the second 3D work is in preparation, but we almost finished it. So we analyzed the superarcade downflows in up above the flare loops. That's the observations. That's the theoretic models. So in this model, we have like erupted flare loops, flare loops, and that's the current sheet inside. And underneath, and we have like a plasmoid here, and the SAD structures formed because the shrinking flux tube found here, and we have the wicks of the tube correspond to the large void found identified by SADs. So that's our simulations in 3D. We have like a flux loop here and arcade here, and that's the current sheet. And we have found 3 different kind of blobs that have very different connectivities. That's different with models. So we analyzed what happens to the how the guide field affect the formation of the SADs. So that's the guide field at different slices, and that's the density and the pressures. So in different guide field, we have very different evolution of the density and the pressures. That's the SAD in the static images. We can observe the finger-like structures in different wavelengths. That's very alike. And with the help of simulations, we can track the loops shrinkage in 3D. So we track like one specific loop originated from the foot point here. That's the right line. So that's the before reconnection, and that's the flux just reconnected, and that's the shrinking processes. So we plot the time, the time and the space of the different variables. That's the So the horizontal axis correspond to the distance along the specific loop. So we can observe that here a lot of informations. So we have like reconnection outflow regions and the higher density regions because of the shock and here we have the heating from the loop, and also we have observed the atmospheric evaporations from the velocity parallel to the local magnetic field. That the negative velocity means the motions to the point, and the positive means the motion to the apex. And here we also observed slow shocks, discharge shocks from the reconnection, and also slow shocks from the shrinkage of the loop. And so finally we analyzed the instabilities. We analyzed the RM and the RT instabilities in the early stage of the eruptions. That's the black dots mark the positions where the RT instability occurs. We can observe that it's highly dynamical, so it's have no time to evolve for this. No enough time for evolve for this instability. So we tend to catch instabilities. That means that should have the shear velocity in the flare loops. We calculate the local project Mach number, which gave like these two values at the interfaces. So the condition is that so the KH instability occurs for the case M greater than 2. So that means in our case it's satisfied. And we also calculate the time scale of this kind of instabilities only 6.2 seconds. So in our general simulation is about 1,000 seconds. So it's always dominates in our later stage of eruptions. Okay, so here comes conclusions. So for these three subjects, we did several things, and before it's mainly in 2D. So right now we focus on 3D, and also the shock. So we want to do 3D simulations. So in the future, we also will include the particles in the 3D MHD simulations to conduct a comprehensive study of solar eruptions. So that's all. Thank you.
Thank you. Do we have any questions from the audience here? There, no?
I was a little surprised by the statement that you were getting dissipation at MHD scales, because usually turbulence cascades down to kinetic scales.
Yeah.
Dissipate, but that actually did more of an inverse cascade than the dissipation scale.
Yeah, could be inverse cascading. Could be the one reason of that, and also we have like the slow shocks to dissipate the energy at the MHD scale. So also yeah, that is two reasons. Slow shocks and also inverse cascading could be the reason of that. I believe so.
Yeah, I mean, you quoted the resolution on the simulations as 20 kilometers, correct?
No, that's different. Different model use different resolutions. So not always.
So the ones that I remember asking where you were showing dissipation happening on 100 to 200 kilometer
Yeah.
scales, right?
Yeah.
Did you say the resolution for that was 20 kilometers?
Sure. Yeah.
Well, I just think that's numerical issue.
No, at beginning we also thought could be the numerical stuff, but we found that the physical processes corresponding this value. So that means we found the ways of the secondary current sheets between the merging plasma point. That corresponds to this.
I mean, you can find another physical length scale that may correspond to that dissipation, but it's much more likely that I would say that it's numerical dissipation if it's just on a few times the length of your resolution element. I mean,
Yeah,
you expect to see dissipation there. I'm also sort of surprised that you're putting these magnetic Reynolds numbers of 1 million when your simulations are a few thousand squared. I mean, did you run simulations at magnetic Reynolds number of 100,000 and 1 million and show differences between them? Are you showing sort of resolve for
the highest Reynolds number we got is 10 to 6.
Yeah.
So the resolution in our case could be enough to solve this equation. That's not, that means the physical one will dominate, not the numerical one.
Maybe you're using a different definition for the magnetic Reynolds number, but if that's sort of the ratio of the dissipation scale of the magnetic field to sort of the energy containing scale of the magnetic turbulence, then that can't be more than your resolution.
It's complicated to answer that. We use the Lindquist number rather than the local magnetic Reynolds number. We just analyze we also calculate the effective Reynolds number during the real simulations, but we got almost the settled one. So
you calculate the effective Reynolds
number?
Sorry, it's maybe technical, but
yes. That's we in 2D we just calculate the like from the induction equation we calculate the magnetic potential to calculate that. So we suppose that there's a term corresponding to the diffusion and the numerical diffusion. So we compare the physical one with the numerical one.
We're running out of time, I'm sorry. But are you staying here this week at the CfA?
Yeah.
So please, if you have any further questions, we have the Google spreadsheet link thingy. So please use it to schedule a meeting or a chat or something. Thank you.
Thank you.
And thank all of you. We'll see you again next Wednesday.